Hey everybody, it's Dr. Morgan. I'm coming at you from my lab today. Just a really quick, low-quality video that I'm just shooting from my laptop to give you a preview of what we're going to be talking about for the next at least week, maybe a little bit more. We talked about the Big Bang. We talked about some of the evidence for the Big Bang. We talked about the dark matter problem and the dark energy problem, the things we don't quite understand about the large-scale structure of the universe. One of the things I said that we don't currently have any really good answers about are the conditions of the universe at the very, very beginning, the instant of the Big Bang, although we can get very close. That if we look at the history of the universe is smaller and smaller and smaller into some singularity that we don't understand because we can't understand singularities. That's the whole point of singularities. They're a place where basically our equations are giving us a divide by zero error or an infinity. So the question of what's going on at the moment of the Big Bang singularity is and may always be a mystery. We'll, at the very end, talk about whether I personally believe we'll ever have answers to those questions. When we are looking at the cosmic microwave background radiation, we're looking at a particular point in the history of the universe, and that is the point at which the universe went from being opaque to transparent, and that light from the CMBR, that microwave background radiation, is coming from a time something like 300,000 years after the Big Bang. We'll call that AB. Before that, what was going on in the universe? Well, why did the universe go from being opaque to transparent? One of the reasons is that hydrogen, ionized hydrogen, remember, what is hydrogen? Hydrogen is just the simplest element in the periodic table, right? One proton, one electron. In hydrogen gas, that proton and electron are bound together into a closed system. The electron stays near the proton, and that's an atom. If you bang that electron hard enough with either another electron or another hydrogen atom or a photon of light, you knock that electron loose, and that electron can go do whatever it wants to do, and that's ionized hydrogen. The electron in a hydrogen atom, we talked about this when we talked about spectroscopy, can only absorb certain wavelengths of light. But if we ionize the hydrogen so that electron is free to do whatever it wants, that electron can absorb any wavelength of light. So before recombination, when all the hydrogen in the universe was ionized, all of those electrons and all of those protons could just absorb what any light was around. And so light could only travel from one particle to the next particle, and then it gets absorbed and it doesn't go anywhere. So when the universe was all ionized hydrogen, it was opaque, and so we can't see any light. That was before that. As we go further and further and further back towards the Big Bang event, we get a situation that's denser and denser and denser, hotter and hotter and hotter. So we go from hydrogen to ionized hydrogen to what's next. Before that, the universe was nothing but protons and electrons just banging around. What happens if you go hotter than that? What happens if you bang two protons together really, really hard? Well, from the, say, 1900 until 1960, we thought of protons as being elementary particles, that atoms are made of protons and electrons are elementary, they're fundamental. Well, that turns out not to be true. A proton has stuff inside of it. If we zoom in on a proton has three particles inside of it. So does a neutron. Those particles are called quarks. A proton is made of three quarks. Those quarks have nicknames of red, green, and blue. And I'm going to draw them as red, green, and blue, even though quarks are not red and green and blue. Quarks don't have a color. They're not little bouncy balls. They are fundamental particles that we believe are irreducible. They don't have parts. They don't have things smaller than them. But if I bang two protons together hard enough, say proton 1, proton 2, proton 1 is made of three quarks, proton 2 is made of three quarks. If I smash them together hard enough, and we know this is true because we can do this in particle accelerators on the Earth, red, oh, that's orange, that's not one. There's no orange quark. There's only red, green, and blue. We never see quarks, by the way, by themselves. And the reason is that quarks are held together by a very strong force called the strong force, the strong nuclear force. And it turns out you can't pull two quarks apart from one another and pluck it out of a proton and look at it by itself. But if I bang two protons together hard enough, I can knock the quarks loose from their particles that hold them together, which are called gluons, and make a plasma of quarks and gluons. That's called a quark-gluon plasma. How do we know that you can do that? Because we have done it in particle accelerators here on the Earth. What does that mean? That means that at some point in history, there was hydrogen and helium and stars. At some point before that, there was nothing but hydrogen atoms. At some point before that, there was nothing but ionized hydrogen and electrons. At some point before that in the universe, it was so hot that there was nothing but quarks and gluons and neutrinos and individual subatomic particles just bouncing around the universe all by themselves. That means that in order to understand this first few seconds of the history of the universe, we have to understand a little bit about particle physics. We have to know what were the things in the universe at that time. In order to understand the universe today, we have to understand the stuff that the universe is made out of. Galaxies and stars and planets and stuff like that. Well, there were no galaxies or stars or planets 300,000 years after the Big Bang. There was just hydrogen gas. There were no hydrogen atoms a millisecond after the Big Bang. There was just quark-gluon plasma. So I'm going to spend a couple of days talking about what scientists call the standard model of particle physics, which is just a list of all the particles we know about in nature and how they interact with one another. Understanding the standard model of particle physics is necessary because that's all that there was a few milliseconds after the Big Bang, so it's important for that reason. The other reason it's important is because the unanswered questions about the Big Bang event are connected to the unanswered questions about the standard model of particle physics. Standard model makes it sound like, well, I guess we know it's 100% right? Well, no. We actually know it has issues and problems and questions that we don't know the answer to. So in order for you to understand these unanswered questions about the Big Bang, I want you to understand a little bit about these unanswered questions about particle physics, because when the Big Bang event happened, or very shortly after, microseconds, nanoseconds after that Big Bang event, after the expansion started, the universe was hotter than the hottest particle accelerator, the most energetic particle accelerator we can build. The structure of the universe was nothing but individual subatomic particles that had not yet combined together to make protons and neutrons and atoms and the things we see around us today. So that's what we're going to be doing for, like I said, a couple of days. And then I'll try to circle back around to these questions. What can we learn about the very early universe from studying these smallest particles that exist in nature? And it's something that fascinates me. It's the reason I became a physicist and not an astronomer, because at some point, astronomers and physicists are asking the same questions about the same point in time. That Big Bang event is as much a particle physics question as it is an astronomical question. In fact, it's more of a particle physics question because astronomers can't see any of this stuff that happened here. Astronomers can only see light from after recombination. Everything that happens before recombination is up to particle physicists and their accelerators to try to figure out. So that's what we're doing for a couple of days. I might try to find a nice little YouTube video to point you to get a baseline of understanding of atoms, protons, electrons, quarks, gluons, and smaller and smaller and smaller structures. Or I might just start out with a video of my own after this one.